Number. Okay, recording. Good. Okay, so we have established the instruction set architectures, and we know that it's kind of abstractions. It's how the software see the computers. It's how the hardware designer or the architect design the processor to functions. So today we're gonna move on a little bit and see what if we got an instruction set. We got an instruction set. What do we have to do so that we can design a processor out of it? นะครับงั้นง่ายๆคือมีสถาปัตยกรรมชุดคำสั่งง่ายๆมาให้คุณชุดหนึ่งนะฮะแล้วจงดีไซน์โปรเซสเซอร์ถามว่าจุดมุ่งหมายจริงๆคือต้องตั้งใจจะสอนให้คุณดีไซน์เป็นหรือเปล่าก็ไม่เชิงแต่ว่าอยากจะให้คุณเข้าใจว่าข้างในมันทำงานยังไงในเบื้องต้นก่อนนะครับ but the real contemporary architectures like if we talk about Intel's or ARM it's very complex so we start with very simple architectures and very simple implementation. In this case, I refer to it as single cycle processor. Okay, now let's get started. Come on, okay. มันทำให้ใหญ่ไม่ได้ไหมมันสุดๆหรอวะน่าจะสุดแล้วนะจอนี่สูงเสียงตึงแต่เซ็ต All right. What is single cycle processor and how are we going to implement it? Let's find out. Let me recap these equations. 2 weeks ago, we learned that CPU times is a function of instruction count times CPI times cycle time, right? Like this. Instruction count IC times CPI times TC. Yeah, just like that. And here I got this little triangle that try to represent instruction count, CPI, and cycle time. If our processor is based on this function, that means you somehow want to minimize them to get the best performance out of it, right? Minimize everything. But we also learned that we cannot always minimize. So before we move on to design the processor, let me recap this idea. Instruction count. What can we do so that we can reduce the instruction count? Optimization, of course, let's compile the things. Or sometimes different architectures, different instruction set architectures would give you lower instruction count. It's like some processor may have very powerful instruction that just one instruction can do several things. Or you as a programmer, you might decide that, oh, you do different algorithms, different software idea, coding techniques, and you might be able to make your program run faster. But if the instruction set is fixed, likely this is a job of compiler and programmer. Okay, like you buy Intel processor, you cannot change the ISA. You buy Apple, the Mac computer, you cannot change the ISA because it's fixed with the processor. So it's a software things now. Okay, so we can say that instruction count now, regardless of, besides the instruction set architecture, just depends on software developers, just like that. How about CPI? Well, even further, you cannot change the CPI. As a software developers, you cannot do anything to this. Maybe I change color. This is the hardware things now, totally hardware, right? Why? Because it's how the CPU organization works that gonna say, oh, this instruction may require 2 cycles, 3 cycles, or 4 cycles, something like that. Similar things, the cycle time, how fast is the clock that we can put to the processor. Why some processors say, oh, I can do 3 gigahertz. Some say, no, 1 gigahertz is more than enough. You cannot go any faster. Back in my day, my first processor was like 4 megahertz. See the unit megahertz, not gigahertz. Actually, some microcontroller, the one that in the controllers, the air condition, something like that, it's less than that. I used to have a processor that used 1 megahertz processor, but that's pretty old. Nowadays, you would see at least 4 megahertz for embedded system, or maybe 20 megahertz, like that. Right? But for desktop, well, at least 1 gigahertz or 2 gigahertz, that's normal for today technologies. So that's highly depends on the VLSI technologies, which is not a part of this class, and the organization. So this chapter here, we're gonna focus on the organizations. Actually, 2 more chapters from now, focus on the organization inside the processor. How does it work? How can we reorganize things, or how Intel or Apple organize things inside that make it fast? It was like that. So we're gonna start with a simple processor. And And in this case, our processor for today would like this. We leave this to the software. We're gonna fix this to number 1. That's why we call it single cycle processor. And this gonna be very long clock, just so you understand how the processor works to begin with. And later on, next chapter, we try to reduce this, try to optimize, I should say. Not already reduce. Okay, are we ready? You okay? So we're gonna play with data card and control. Ever heard of it? Maybe not. Okay, so we're gonna learn about data card and cycle time. And control card, sorry. Okay. Let's try to understand the concept of clock a little bit. Yep, good morning. What is a clock? Well, it's if we refer it to logic design, we got something that we call finite state machine. Ever heard of it? Or sometimes we just call it FSM, finite state machine. Not sure. M, finite state machine. Finite state machine. Well, finite state machine basically say whenever a new clock is coming, the circuit gonna change state. So we have clock to trigger the state. And usually it's the rising edge of the clock that we change state. Well, how much do you know about this from Professor Yang Zhao in the circuit class?
Yeah, but
Something ring a bell?
about the finance state machine.
Yeah. Did he?
We didn't really go into the finance state machine, but we did know about the rising technologies.
Okay. You don't know about finance station, but you know about flip-flop state.
But well, yeah.
You know that? Okay. Okay. Never mind. We can talk about architecture by ignoring that you don't know that, but if you know that, it's easier to explain. Okay. So the idea is whenever a new clock is coming, usually the rising edge, we're gonna change a state. See, every new clock we change the state. And in the middle, in between, it's combinational logics and or not basically. Right? Combinational and or not, that's basic thing. So our processor, for the moment, we say, let's make a single cycle processor. That means the clock is, sorry, the CPI is 1. That means when a new clock is coming, we're gonna start new instruction. Say that again.
With the state change from 0 to 1, give the instruction of the
For this example, for this design, when the state change, we gonna issue a new instruction, start a new instruction. For now, okay. But as we move along, we would say that, oh, sometimes we use several clock or several state for one instruction. But just to simplify it for the moment, one state per instruction, like that. Okay, so we're gonna learn how to make data part and later the control signal. And it's like general concept of the design. Oh, I got something that some specification that I want to design. Okay. Let's try to understand the specification. Or in this case, we say analyze the instruction set architecture. Determine the components that we might need. Okay. And then step number 2, try to construct the components. Number 3, assemble data part. Number 4, let's do the analysis. Oops. Sorry. ครับพี่ อ๋อ จริง ๆ ไม่ควร5 นาทีก็ควรจะเสร็จแล้วพี่อ๋อเอ๊ะไม่น่ามีอะไร ครับยี่ห้ออะไรพี่ โทษที อ๋อ ครับ ครับถ้าพี่ลองเสียบไว้สักครึ่งชั่วโมงก่อนก็บางทีมันก็แบบ deep sleep มันกว่ามันจะกลับมาอะไรอย่างเงี้ยครับใช่ครับใช่ครับครับผมครับสวัสดีครับโอเคsorry about that all right it's if you think about it, the step that we use to design the processor is like the step that we use to design software. You got software requirement, you do the analysis, you do some design, and you coding like that. But this is hardware, similar. Mhm. So let's try understand our instruction set for the moment. In this case, I use very simple architecture that I designed myself. I call it NanoLada like that. It's fixed length instruction set, only 3 formats. Mhm. This is very simple instruction, very simple instruction set architectures. Just to teach you in this class. So I got 3 types of instruction or 3 formats, basically. The R type, the I type, and the J type. We got 6 bits for the opcode. And depending on the type, some type you can specify 3 registers, 3 operands. Some type you can specify 2 operand and immediate 16-bit. Again, we know immediate from our previous lecture, right? Immediate, meaning you put some number directly into the instructions. Okay? And we got one J type where you can put very long address to it. Okay. Let's see how well is your background in circuit and digital logics. If I have an instruction format like this, my question is, how many registers do we have in this architecture? You can actually answer that from the instruction format. Registers or internal temporary memory, whatever you want to call it, we call it registers. เข้าใจคำถามผมไหม ผมบอกว่าจาก format ของคำสั่งที่เป็นไปได้ใน processor ตัวนี้3 format ผมถามว่า processor ตัวนี้มี register มากสุดกี่ตัว 8? One of your colleagues say maybe 8 registers. Agree or not? Say that again. 8? Why you say 8? Any hint behind that?
Each register is one digit of a binary. So if the 3 digit of binary, I would assume A possible. I don't know. I'll just really
Okay. Let me quickly write something from our previous week. Like when you say add R1, R2, RT3 like this. Okay. It's basically say you add R2 to R3 and put the result in R1. Okay. This would translate to the R type, right? So at the end of the day, you may see something like this. I make up something like this is 6 bit for add, and you would write down something for R1 and something for R2, something for R3, right? So this field RS, RT, RD basically represent R1, R2, R3 in this instruction, right? And how many bits do we have here? 5 each. That means you can use 5 bits to address the register. So with 5 bits, how many register? มีเลขฐาน2อยู่5 bit 2 to the power of really? And that would give you what number? 32. Okay. You got it? So that means if we just take this one out, it's 5 bits. So you can start from 0, 0, 0 to 1, 1, 1, 1, 1. Totally, it's gonna be 32 register,
Oh, I see.
right? Starting from number 0 to number 31. Got my point? Yep. Good morning. Come on in. ทันไหมเข้าใจป่ะ We translate the instruction into binary string, right? In this case, we say we got 3 formats of binary strings. Or just to match with the term, we got 3 format of the instruction. So whatever you write in the computer, in the software, in your programming languages, at the end of the day, it translates into some binary strings, which explain, oh, this is the instruction, this is the operand, the register that we are talking about. And the hardware would fetch this, take one by one, take it in one by one, and do the operation inside the processor for you. Okay, is it better? Try to go slow so you understand. Yep, go ahead. Related to what? 32-bit architectures. Yes. Let me clarify that a little bit, but good question. It's like this. When we say we have 32 bits architecture, it usually means one register, you got 32 bit of data. But in this case, it's just coincident that we also got 32 register, and each register got 32 bits. We got 32 register, but each register can hold value up to 32 bits. That's the one that we say 32 bits architectures. And according to your question, when we say 64-bit architecture, that means each register got 64 bits, but it doesn't mean we got 64 registers. Okay? We good? Oops. Sorry. So we got 32 times 32 bits register for this architecture. because we always have 5 bits to say which register that we want to use in our instruction. You understand the difference between address and the data, okay? We can address our register with 5 bits. So that means we got 32 registers. Mhm.
For the architecture will be reason times 4.
So 64-bit architectures means each register would have 64 bits. Mhm. But if this is 64-bit, but we still use the same instruction format, that means we got 32 registers. Each one got 64 bits. Yes. Mhm. Okay. Anyway, as we move along, you will see more examples. Mhm. So we got 3 instructions formats. Mhm. And for this design, we got quite a few number of instructions. So I give you 5 instructions, very simple processor. Only 5 instructions, okay? We're gonna learn how to make processor from this instruction set with 3 instruction formats and only 5 instructions. Pretty lightweight anyway. So let's see how it works. We got first instruction, we call it ORI. ORI. What is ORI? To explain the instructions, usually they would have some kind of pseudocode, but we got a special word for it. We call it register transfer language, RTL, to explain the instruction. Okay, we got instruction ORI. What does it do? Well, it's gonna use register from RS, indexed by address by RS, all that with the 16-bit immediate. Then put the result back into register RT. So how would it work? It's like if I write something like this in assembly language, like all R1 with register R2, and I'm gonna write immediate 5. If the opcode is like this, let's translate this into the R type. The I type instruction format. So this one would translate to what? 0, 1, 0, 0, 0, 0. That's for the opcode. And then go back. RS first, okay. RS gonna be number 2. So we're gonna have number 2. All right. Then the target gonna be number 1. Right? And number 5 gonna translate to it is lazy 101. That's number 5. So whatever you write in assembly language would translate to binary string like this. That's basically what it says. And when the processor took this one in, took this instruction in, this binary string in, it's gonna do the OR operation and write it back to another register. So this is how instruction work from the processor point of view. You just specify binary string, processor read it in, and oh, you basically want me to do this, so I take that number, do this operation, and write it back, done. Yes, please.
Each professor will have to choose either one
For each instruction, it's gonna specify the type, each instruction, yes. But for Intel, you may not see R type, I type, J type. Intel would have different kind of format, but I just simplify it for the explanation. Mhm. The,
can have one.
yes, yes. Intel got like 20 types. That would be too difficult to teach you anyway. Uh-huh. Be good. I try to go slow again. If you have questions, let me know. Okay. What else do we have? We have ORUI, actually short for all upper immediate. The difference is that this one use zero exchange, this one use zero path. Okay, we're gonna revisit that. Here we go. Before we go any further, do you have any idea what is this for? PC equals PC plus 4. Yeah. What is PC? Do you know? In this case, it's just a register program counter.
So I want to translate our assembly code into the RTL assembly code.
We use the RTL to explain how the processor works for each instruction.
And the actual binary is the quantum sequence.
Mhm. Okay. Let me clarify this a little bit. Program counter on PC. PC is like this. PC say, what is the current instruction? So we usually use PC to point to the memory. And you get the, in this case, the instruction. Sorry for my handwriting. So think of it this way. When you write program, you got bunch of memory. And first line would be the first instruction. Second line would be the next instruction. Third line would be the next instruction. Right? When you write software, you usually go from top to bottom like that. When we run the software, we have something to point. Oh, we are now at the first line. Let's read the instruction. Then we finish, we move to the next line. Let's read the instruction. When we finish, we move to the next line. Let's read the instruction. And that thing that say we are moving to the next line is PC, program counter.อืมอืมครับครับอะไรเอ่ยครับ ครับครับไม่ตอบครับครับครับผมครับผมครับครับครับครับครับรับทราบครับครับครับครับครับครับครับครับผมครับครับครับครับครับครับครับครับมันจะยาวไหมครับพอดีผมสอนหนังสืออยู่ครับครับครับไม่สะดวกครับครับครับครับครับครับเดี๋ยวค่อยคุยได้ไหมพอดีผมสอนเลคเชอร์อยู่หน้าห้องเนี่ยครับโทษทีครับครับอ่าวันนี้ต้องขอเย็นๆหรือไม่ก็พรุ่งนี้เลยครับโทษทีครับครับครับตกลงต่อสุดท้ายปี68นะครับติดสัญญาหลังจากนี้ครับครับครับครับครับsorry okay so we got all upper immediate and add okay add so what is add it now R type so how does it work then it's like this when I write add let's say R1 R2 and R3 it's gonna translate to R type which is this right so we're gonna see like that's for the opcode, right? And this is RD, RS, RT. So we gotta have RS Number 2. RT, which is number 3. And RD, which is number 1. Like this. That's for the add. Okay. Example anyway. And I try to explain to you why we need PC equal PC trust 4. Because each instruction got 32 bits, basically 4 bytes. Our memory is byte addressing. That means each instruction got 4 bytes. When you want to move to the next instruction, you have to add 4 bytes to get to the next one.
And you're talking about the best one.
Oh. Okay. Let's say you got register pointed by RS. And you got immediate, which is 16 bits here. When you say OR, OR, it's logic OR. So what is OR? It's like if you have like this, and you have OR 1 and 0, you get what? 1. 0 and 1, you get 1. 0 and 0, you get 0. 0 and 1, you get 1. It's basically OR. So ORI, since we only have 16 bits here, we're gonna fill it with zeros and do the OR. That's for the ORI. OR with an immediate. And the ORUI mean upper immediate. So it's similar, but it's gonna be like this. You got a register, but rather than OR with the lower bit, we're gonna OR with the higher bit. So it's OR here, and we fill this with 0. So just different part of the immediate. We see that, but you got the idea. Just we got 132-bit numbers, and we got 16-bit immediate value. We want to OR them together like that. It's logical OR. อ๋ออะไรเนี่ยเดี๋ยวนะมันเรื่องเยอะจังครับพี่อ๋อผมสอนผมสอน ICE อยู่พี่ผมไปไม่ได้เสร็จเที่ยงเลยครับอ๋อครับขออภัยให้ครับครับ Okay. What else do we have? We have load instruction. Basically say go grab data from the memory and put it into the registers. and store, do the opposite, get data from the register, put it back to the memory. All right. Okay. 2 more instructions. Branch and jump. So we got only one branch instruction. Branch if equals EEQ. Branch if equals. Basically say if RRS equal to RRT, let's make a jump. And how the jump work? Well, it's basically just add some number to the PC, right? Since I told you earlier, PC means where is the next instruction? If PC plus 4 means the next instruction is right behind. But if you want to jump in, oh, add some number, so we go further or go backward like that. Yeah. Yes, and we're gonna talk about that. Yes, of course. Okay, this might be pretty new to you because you are not familiar with the concept of logic design anyway, but I try to explain. Mhm. All right, so I gave you what? 7 instructions so far. 3 instruction formats with 7 instructions. From the requirement, from the register transfer language here, we can say what kind of components do we need in our processor. All right. Oops, too fast. Mhm. So let's try one by one. We got registers. We got register. And I already told you we got 32 bits registers. All right. Times 32 registers like this. How do we know that? Because it's indexed by the RS, RT, and RD, and we know that we got 5 bits. That's what I told you earlier. So we got register. That means to implement this processor, we have to first design 32-bit register with 32 registers. All right. What else do we need? We need PC, a special register that say, where is my instruction? Line number 1, line number 2, line number 3, basically. So we have a register to say, where is my instruction? Okay. What else do we need? We need arithmetic unit that can do at least 2 functions. First, can add, another can do OR. right? We only got add instruction and or instruction. But again, in the processor, they can add, subtract, or and several things. This is simplified version, only two operations. Add and or. We need an adder to do basically PC equal PC plus 4. So we need adder for that. And the extender was we just have what? Zero path, right? Zero field and sign extend. We're gonna explain this later. We'll get to that. Okay. Okay. Let's try to design it one by one. Registers. 32 bits, that means we need 32 flip-flop to make 32 bits. Right? And we got 32 register, that means we need 32 sets of them. ถ้าวาดรูปนี้เข้าใจว่าหรือยังงงอยู่ flip-flop 32 ตัว เอามา32 ชุด ชุดละ32 ตัว32 ชุด ตอนเรียนเซอร์กิตมีภาพอะไรงี้งอกๆในหัวบ้างไหม You got the concept from circuit class, right? You should. Right? And we must be able to read two register at a time. Right? งงไหมฮะ We must be able to read two register at a time. Why? Because if you take a look at the instruction like add, we must be able to read RS and RT at the same time. So how can we read from two register at the same time? We add two multiplexers and select 32 register from the 32 set. So this is like you can put RS here or put RT here, and you got two register here like RRS, RRT here like this. Got my point? Lead to registers. Then write back to one register. This is the data. And to write, this is the address. So you basically put RT here, and we're gonna have data writing to whatever register that address back RT. ถามจริงยากไปไหมงงไหมฮะจริงๆแล้วคุณควรจะเรียนเรื่องนี้จากเซอร์กิตไม่ใช่วิชาผมคุณต้องรู้เรื่องพวกนี้ก่อนมาจากเซอร์กิตนะถ้าพูดตรงๆ All right, keep it simple. You got magic box that when you put some number in and you get data set that you want. Think of it as an spatial array. Okay. Don't worry about the internal parts, how it connects. Okay. Just ignore it.
That added,
Which one?
the top left,
Top left, this one? Decoder.
but what do you write? I can read it.
Write register. Address ADDR. ADDR address.
Oh. And the bottom one,
Bottom one data. Okay, sorry for my handwriting. I don't like writing on the screen anyway. I don't like it. รอดไหม You can do it. You can do it. It's not rocket science. You can do it. ผมพยายามไปช้าๆนะเนี่ยคุณช่วยให้คุณเข้าใจมากขึ้นหรือช่วยให้คุณยิ่งว้าวุ่นกัน Again, don't worry about the internal component. Just think of it as a spatial array that you can read two numbers at the same time, and you can write one number in. Okay, just like that. คุณมีกล่องมหัศจรรย์เก็บของได้32ชุด สามารถอ่าน2ชุดออกมาได้พร้อมกันนะครับคุณก็ต้องบอกเอาชุดที่0ชุดที่1ชุดที่2 okay just like that put in some index and you got two data at the same time you can write to one data but you have to say where do you want to write and this is the data just like that okay if you really want to know to learn how does it work the circuit class should have taught you earlier okay this is the first component register file the first component register file okay next component the extender okay I would assume that you know the negative number in binary do you know how we represent negative number in binary two complement okay good รู้จักเนาะ again it's not my class right you should have learned from other class another class okay let me ask you this question simple version actually let's say I got a number like this how much is it นี่คือเลขหาร2ถูกไหม this is binary what is the value of this number number 3 okay what if I write something like this what 11 what if we have signถ้ามีเครื่องหมาย in true complement format
ก็เป็นที่ต้องเป็นจุดที่ต้องการ
in binary in true complement how much what is the value of this negative 5 negative 5 okay actually this is how it works right แบ่งเป็นใช่ไหมแบ่งเป็นนะเป็น okay just recap knowledge from previous class all right Mhm. This is basically number 3 in base 10 this is basically -5 this is 4 bits right what if I want to make it 8 bits what do I have to do this is 4 bits right I want to make 8 bits extend that to 8 bits what do I have to do
Use that combination.
for number 3 basically write 0 how about -5
One. That's where,
see that's sign extension basically this is the sign bit okay let me change the color this is the sign bit you extend it see so when we say sign extender basically you get the most significant bit and copy thatเข้าใจยัง sign extend ทำไง so sign extend basically you extend the sign bit and for us we have 16 bit immediate when you do sign extend here's the sign bit just copy that right this is the sign extend B how about 0 extend
all that we will see.
extend it with 0
Also, yes.
and for 0 pad put 0 at the end
Adding is very it's full as a
say that again
adding is good at the end.
padding pad to the end
To the start.
Yeah.
That's the start. Yeah. It's
It's in the with number by
longer.
space.
it's like you got 4 bits you want to make it 8 bits so make it extend the bits Mhm.
So like if I want more digit, I just extend it.
อือฮึทำตาปิบๆไหวไหมลูก This is fundamental actually like I told you you should have learned it from another class not my class I just put it in hardware perspective all right this is extender what else the memory well without taking a look at the inside of it think of it as a big array where you put the address in, you get the data out. And when you want to write to it, you put data in and you say, I want to write to this address, like that. Big array, basically. But in low-level architectures, we don't have dimensions, only one dimension for memory. Okay? What else? ALU. Okay, I try to write something, but again, if you do not understand it, that means you have trouble with the circuit class, not my class. But I just write how should it works from the hardware perspective, okay? Add, how we do add in the processor. How you add two numbers together in binary using circuit.
check the present.
Yeah. You know the full address? You know the full adder? Or do I have to write the full adder for you? เคยเรียนไหมวงจรบวก full adder
It's small page, right?
yeah
That's what when uncheck and the page small.
oh okay you got the idea yes okay it's like this again this is simplified version we got full adders what is full adder full adder got two input A and B and carry in right C in and you got the result carry out and C like this right this is for one bit right and we say our ALU must also be able to perform OR so we have OR right right uh-huh. But we also say we want to do subtract. So from the logic point of view, it's like this. This is for one bit. For one bit. And then we have 32 bits, so you have 32 copy of this. Okay. Anyway, if you don't understand it, just leave it. Just leave it.
Me and I see
You should learn that from circuit class, not my class again.
remember
คุณเรียน circuit เทอมไหน
เทอมที่สองว่า
เทอมที่แล้ว
เทอมหนึ่งปีสอง
เทอม1 ปี 2ตอนนี้อยู่ปี 3ใช่ไหมนี่คือปี 3 เทอม 1ใช่ไหมนี่ก็ผ่านมา2 เทอมเองนี่3 เทอม
สามอาจารย์ สามพวกเทอมนี้สี่เป็นแบบอาจารย์ตี
อืม
อาจารย์เรียนตีไปเรียนไป
ฮะ
อาจารย์เรียนจบไม่ได้เรียนแบบ
Okay, this is from circuit class anyway, but we use the knowledge from the circuit class to decide ALU. Okay, okay ดูสบตาพวกคุณแล้วช่างมันเถอะ Okay. All right. Let's assume that somehow you managed to design the processors, sorry, the registers, the ALU, the program counter, the extenders, okay? You manage to have them up. Now let's try to make data part for the processor. Ready? Okay. จะรอดไหมเนี่ยแต่ละคนนั่งอึ้งเงียบกระพริบตาปิบๆagain we have times to understand this okay let's start at the first instructions first thing first we want to be able to fetch an instruction so to fetch an instruction you put PC to the memory put PC to the memory and the memory would give you the instruction Analogy is like this. Oh, point to the first line. That's my instruction. So I read 4 bytes from the first line. That would give me my first instruction. So PC point to the memory. Memory would give me instruction. Right? And we also have to do PC plus 4. That means we have to put in an adder. Right? And plus 4. Right? Good. But the tricky part is, if you see, I leave the 2 least significant bit as 0. Why? And I choose to do plus 1 to the 30 bits. มองออกไหม It's like this. This is 32 bits. 32 bits. Right. Plus 4. 4 is like this, right? This is 4, right? So plus 4, what does it mean? It means the last 2 bits never change. It's like plus 1 to the after 30 bits. Right. So we minimize the circuit a little bit and say we only need 30 bits and plus 1. งงไหมฮะ เหมือนผมมีเลข1ตัวฐาน10แล้วผมบวกทีละ10อะผมบวกหลักหน่วยช่างหัวมันดิผมก็บวกหลัก10ไปนึกออกปะอันนี้ก็บอกเรามีเลขฐาน2เราบอกเราบวกทีละ4งั้น2บิตสุดท้ายก็ช่างมันสิก็บวก30บิตบนไป Okay. So this gives you PC plus 4 with smaller circuit. Just like that. Okay. Let's try these 2 instructions then. Or the RTL say read data from RS, all that to the 0 extender of immediate. That means you have to put RS to the register files. You would get RS here, right? Now you want to all that with immediate, so you put immediate to the extender. Now you got 32-bit, feed that to the ALU and ask the ALU to do the OR operation. Then the result, write that back to data. So this is a data part that would allow the processor to perform all. And you write to what? RT. So we write RT here. Let's not have a break today, but I let you go maybe like 20 minutes early. Would that be better? Okay. Let's not have a break and I let you go earlier. Okay. Mhm. All right. And again, can this data part perform the ORUI? Yes or no? Okay, let's follow it. RRS, this is RRS. Okay, good. Zero pad, yeah, zero pad. Oh, okay. Right back to RRT. Here we go. So the same data part work for both ORI and ORUI, right? Data can just follow through and write back the result. That's why we call it data pattern, data flow to the lines and then get back. Okay? Yes.
From the ALU, right, into the RT.
It right back to the RRT, yes, because we specify RT here as a place that we want to write.
Sorry, that.
I don't understand your question. Say that again.
What the top one?
The what?
Like, I understand that the right level for the ALU also move on. But it's the top of the.
What is the top what? Top left block, this one, register file. Register file, which is back here. This one. Okay. So we got the register file as a component and we just use it here. Okay.
For me to be why I want to like just 25 zero extension.
Yeah, zero extend and zero pad. Yes.
At the beginning. It's not at all, right?
Yes. Are we good?
Can you tell me what's the U stand for?
upper,
Oh, and I,
immediate,
imminent.
immediate,
Oh, imminent.
or immediate, yes, or with immediate.
Or imminent, or imminent.
We good? Can I add another instruction to this data part? Okay, so next instruction that we want to add is what? Add. Okay. Let me try to put add here. Actually, the result would be in the next slide. Okay, but let me draw on this one first. So you understand what is the process of my thinking that we get until we get the result. Add is like this. Okay, you add R equal okay. Let me draw this for now. Well, in the past, I usually write on the blackboard, but since we do the recording, writing on the blackboard will be nonsense here. Okay. We say we want to do the add instruction, but again, our data path must also be able to do the OR and the OR upper immediate here. Okay, so how to get the RS and RT and feed that to the adder? That means, oh, I also want to read here, and you would get this would give you what? RRS, and this would give you what? RRT. You want to add, that means you have to feed this to the adder, right? The ALU, but wait, we already got the immediate in, so we need multiplexer to select just one line. Right? And when the data flow back, we got the data, but wait, I want to write to what? RD. So that means not just RT, this has to be again multiplexer, and it can be either RT or RD. The result is in the next slide. This is just the thinking process of when I add another instruction in. So I have to make sure the data path can also do the previous instructions and add one more instruction to it. The data can still flow and get me the result that I want. Okay, so in the examination, just use pencil and rubbers. You might want to change it several times, so use pencil and rubbers, okay? I just to check your understanding, I may give you the components, some kind of instructions, and say, give me the data part, like.
Like I ran the arrow on the formula.
อ่าฮะใครไปรู้วันหนึ่งพวกคุณอาจจะไปอยู่ Intel อยู่ Nvidia ก็ได้สอนคุณไว้ก่อนดิเดี๋ยวทำไม่เป็นเว้ยเดี๋ยวไปสมัครงาน Nvidia แล้วก็ไล่ออกมา Yep, go ahead. Oh, when you put in the multiplexer, multiplexer say basically say we have two choices. You can connect here in the green or connect here in the blue. So what say that I want the green or the blue is the selector here. If I put in 0, I would get the green. If I put in 1, I would get the blue like that. Just like selector switching. Just put some label to the line and we're gonna connect to it later.
What is MUX?
Multiplexer. short form multiplexer ชื่อเล่นของ multiplexer เขาเรียกว่า MUX MUX นะฮะ so MUX short for multiplexer PLEXOR and you might wonder why we call it MUX this is MU and X from the again you should have learned this from circuit not here no idea at all huh okay maybe I should talk to who อาจารย์อะไรหยางเจ้า
It's also for like full class.
to class and who is your professor อาจารย์หยางเจ้า okay maybe he focus a lot on the analog part
Yeah.
uh-huh. but if you ask me the important part for the computer is actually the digital circuit maybe he didn't spend enough time for the digital circuit anyway not his fault but maybe I should talk to him we need more of that
What does like people who want mean like inside the AUX?
Oh, we have several types of multiplexer and usually 2 to 1 mean you have 2 input, you want 1 output. Okay, now we have to add one more instruction in this case, the load. How does the load work again? And let me quickly switch to that. A load, yes, not slightly. So it's like this, load, right? It's RT equal MEMS RS plus okay. Yeah, just shorthand for that. I want to read from the memory which address the addition of RRS and the sign extended immediate. Use it as an address and then write it back to RRT. Okay. Let's try drawing the data part. Now we can use red for now. What do we want? We want RRS add with sign extended immediate. Okay, we put RS here, we got RRS here. That makes sense. Sign that extend immediate. Just follow through here, and we got what? Sign that extend immediate, right? So we got RRS here. Add them together, we got this, but wait, we want to use this as an address for the memory. So actually we would have memory and use this as an address, right? Memory. And we have the result. We want to write back to the RRT. That should work. So we just need multiplexer.
How do we get that? Just to get like isn't that thing somehow able to the result of the
Thing that come out from the ALU is the operation that we do on RRS and the sign that extend immediate here, right? Yeah. So you feed it in, you get the result. We'll say we want to use that result as an address for the memory. So I feed that to the memory as an address. Okay.
So that we're passing addresses, not passing like values.
We want to use that as an address, yes. So put it in as address.
For example, if we do like 5+3, then we use 8 as an address,
Mm-hmm. Yes.
and then 8 is also a value. How
Some instruction we might use 8 as a value, but for this instruction we use 8 as a address. That's why we need multiplexer and say, in this case, we want to use it as an address for the memory and get the data from the memory. Maybe you see the next slide, you see better picture of it. Beautiful picture of it. Okay, so when we say we want to use the result from ALU as a value, you connect this. But when you say you want to use it as an address to the memory, you connect this. Right? We have multiplexers to see which one do we want. บ่อยไหมคะทำหน้าเบ้ใส่ผมเลยบ่อยไหมข้างหลัง ยิ้มแห่ๆไปว่าอะไรลูกสายหัวไม่เอาแล้ว Say that again. LW load word. Load word. Load word. Load word. Because for byte of data, we usually call it a word of data. Word, 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 word. Load word. ไม่ชอบเขียนจอเลยเขียนแล้วลายมือเละเป็นโจ๊กเลยแบบเพื่อนผมก็บอกว่าเขียนที่ไหนแกก็ลายมือแย่อย่างนี้แหละไม่ขึ้นกระจอหรอกเคยเห็นลายมือหมอไหมผมเห็นลายมือหมอแล้วผมรู้สึกว่าผมลายมือสวยแต่ไอ้เพื่อนวิศวะเพื่อนคณะอื่นผมก็บอกว่าแกอีกนิดนึงแกก็เป็นหมอแล้วหมายถึงว่าลายมือนะด้วยลายมือ Well, the physician, the doctors, when he want to write something like paracetamol, he would write something like this. Paracetamol. Yeah. So mine is much better, right? You can still see old AD, something like that. All right. Now what? Add another instruction again. What do we want to add? Store what? SW. What does the SW say? Well, it's actually the opposite, right? Of the LW. Right? Yeah. Okay. Right? So check the data part. We got what? RRS here. Okay, RRS. We got sign extended here. Okay, good. Now we got the result, use at an address. But what else do we want? We want the RRT as a data here. So tap it from B and put it here. Now we got data part for the store instruction.
basically just to save the thing into
To save the thing into memory, right?
but why only from B, not A and comma?
Because we want it from RRT, and RRT is here, right? On bus B. Right. And then ยังอยู่กับผมไหมหรือไม่เอาแล้วนอนดีกว่า ชาเขียวก็ไม่ช่วยนะอันนี้อืม Too difficult? No, this is easy. This is nothing. Just that you didn't have enough experience with digital circuit, and so this is the first time that you see something like this. You say, "Oh, what?" But this is pretty basic things actually. Okay, all right. Let me turn it to the beautiful pictures with the store instruction. Uh-huh. And in case you wonder, this is store word SW. Still good? May I continue? Okay. Uh-huh. Okay, let me just flip the slide and explain from this one because lots of detail for the brands. Mhm. So for the brands, we have two choices for PC. One is we do the normal PC plus 4. Another one is we also have to do PC plus 4 plus design extension immediate time 4. So we got design immediate here, extension here. On one hand, we want to be able to do the PC plus 4, which is plus 1 here, so we feed 0 in. But when we want to do the branch, just connect here and we get the branch. Branch is equal, yes.
Basic.
ไอ้พวกตัวย่อสั้นๆใน Intel ก็ใช้อย่างงี้ฮะของ Intel ปวดหัวกว่าอีกIntel ใช้อะไรนะ jump if equal ใช้ JE jump not equal JNE เออ jump if greater or equal JGE อะไรเงี้ยผมปวดหัวเนี่ยนี่ simplify แล้วอย่างที่บอกนี่ยกตัวอย่างง่ายๆมาให้ Okay, and you have to do the comparison. S equal to RT or not, which we can do later. And last one in the series, jump. Jumps mean you just put the address to the PC directly. So we add multiplexers here and put it directly to PC. So now PC can either be the result from the adder or result from the address. And put them all together, you would see something like this.
I can go back to the BGQ.
BEQ, okay, yes,
For the plus line extension,
yeah.
you see on the top line.
This is PC, yes.
Sign extension,
Sign extension here, yes.
and then plus four is the one.
Plus 4 is here.
And then what about the second one, the B1?
This one? Oh, this one basically 30 bits of zero. So this is zero basically.
Basically, no sign extension and sign extension.
Uh-huh. Okay, good.
From the job. So first of all, in the right people understand that it includes the intermediate value. And to cover this, you can see that it includes like the zero extended average. I'm confused, like, is this also like different, like, it's like thing of it?
Immediate value, yes. This is.
We just call it address.
We use it as an address. Uh-huh. Mhm. Yes. Are we good? Still good? So let me recap this again, okay? When we decide the data part, it's like this, you got a quick requirement, but the requirement would come in, they would expand your requirement with RTL, the register transfer language. Like basically say, oh, the OR instruction would do this, the add instruction would do that. Mhm. Load instruction would do this, branch would do that. They would tell you something like this. In the processor manual, they would give you the RTL, the register transfer language. Explain what happens. Okay. To design the data path, basically you go from the RTL into data path like this. Can you do that for me in the examination? This means yes or no? What does it mean? Yeah.
We need to also connect to an extra extender. It's the zero extender. Yes.
Because if you take a look at the instruction format for the jump, let me move back. I start here. We got only 76 bit, but our address is 32 bit, so we have to add something or extend something in front. Yes.
An extender, like, and
Yes, actually we need another extender for that. Yes, the answer is yes. I just ignore that to simplify. Yeah, yeah. We could. Okay. Now we got the data part. You might want to practice a little bit to get ready for the examination. Okay, this is the first time that you see it. Might be lots of information for a day, of course, but like I told you, this is nothing. This is pretty basic things.
If we want to learn one, should we look into like digital small things that get people to make that?
Or you can just practice from my slide, or I got exercise for you later, which you can do that. Mhm. Uh-huh. But what I want to point out here is that from the data part, you would see that we got several control signals here. Let me just circle that. Okay. And actually, we got one more. And one more. Right? This is basically the switching signals that say, oh, now I want to write to the memory or not, or now please select which line to pass through the multiplexers. Most of the time it's multiplexer anyway. Or which mode of extender that I want to use, right? Or what operation that I want ALU to perform for me. Right? If you think about it. We call these signals, the switching signals here, we call it control signal. So I just write out the control signals. Basically the things that I circled from the previous page. Okay, this is the control signal. Now what to do with the control signal then? You have to map the instructions, the input to the control signal. And usually we would do it with a table like this. Still confused, right? Okay, let me go back a little bit. Let's say I want to do the signal for all instruction, the all immediate instruction. All immediate instruction is like what? RRT equals, I'm sorry, SI RRS, or with what? With the zero extent immediate, right? Okay. So what kind of control signal that we have to put in so that the data part can do the all immediate instructions? Okay, let me write that for you. So we got RRT over here. We have to do nothing. Now, sorry, RRS over here. We have to do nothing. This one, we want to make it zero extent. So we have to put zero extent here. And for this multiplexer, selector B, we want to put 1 to get this line. Right? For the ALU op, we want to put the all instruction, whatever the number, the code it is. Then for the select data, we want to put number 0, so we get here. Right? Now we want to write back to what? RRT. So we want to put 1 here. That way we get here. See, we just switch the data part, do the switching until we say now the data part can do the all instruction. And that's actually the first flow here. You following? Yes. Oh, we're gonna have a state machine to control it inside the processor. That's why I mentioned the word finite state machine earlier. So we actually build the data path and we build the state machine to control the CPU. The data path, not the CPU.
Store all the labels into the.
Uh-huh. So as simple as this is, the CPU in general, it's just digital circuit, a bunch of digital circuit. And we repeat the step again now for what? For the ORUI. And if you look at the data path, the difference between OI and ORUI is we change from the zero extent to what? Zero path. Right? And we get the ORUI. And if you take a look at the second line, you will see the difference is, where's that? Maybe I missed a column here. Sorry. You repeat the step for other instructions, right? Okay, maybe I do the add for you, right, so you understand it. Add. Let's try to make a control signal for the add instruction. Okay, for the add, we want what? RRS with RRT, so we want this to be 0. Right? Get the result. Here. Write it back here to what? To RRD. So we want this to be 0. That's for the add instruction. See, just switching. So multiplexer, in a sense, just switching. And you keep repeat that until you got all instruction that you want. Finish the table. We good? Still good? Or you have trouble following now? À, ทำตรงไหวไหมต้องไหวแหละงั้นก็ทำไงไปถอนเนาะก็แปลกๆเนาะ Right? Yes.
And they're off.
It should be extended off. Maybe I cut the table and I cannot fit it in, so one column is missing. In case you don't know, the X mean don't care. X mean don't care. Whether it's 0 or 1, I don't care.
Things like the, especially the branch, I think that around this.
So it's like this when we do branch. Okay. Glad that you asked. when we do branch, it's actually like this. You feed the RRS and RRT here, right? And then you basically subtract them. Subtract them. If this is 0, then it's equal.
So we do this instead of the export.
Say that again.
Like we use subtracting, but we can actually also use like export.
This also works, yes.
Or then we check. Yeah.
Mm-hmm. And that's for the ALU, is it 0 or not? And that's why you have it here. Still okay? Okay. Any more questions for now?
If I'll ask you the personal position.
Mm-hmm. Okay, and I'm gonna quickly walk through this, but again, since you do not have, would say, strong background in digital circuits, you may find this part here from this slide a little trouble for you. But let me just explain it. How does it work? Okay. Usually we would make state machine out of it. But there's one thing that you have to learn is the concept of things that we call critical path. What is a critical path? From the word, it means the path that took the longest, the slowest path. What does it mean when I say slowest? It means actually each component by design, they got delay. They got delay. And if you ask me, how do I come up with the number like 20 nanosecond, 10 nanosecond? It's actually, you have to understand the circuit. If you understand the circuit, you would know that each gate, each component got delayed in it. It's not that you put something in and then you got the result right away. No, they got some delay in it. But if you wait long enough, the data would come out. That's what we call gate delay. But now we have data path, so we have several gate delay from several components. The longest delay that can happen, we just have special name for it, critical path. And in this case, it's the store instruction. Store instruction that got longest path. So you just have to add number together. Oh, this one got 10 nanoseconds. And then what? This got 40 nanoseconds. And then what? The 40s here. Wait for this 20s and go on until you get the result that you want. That's the longest path. And what does the critical path say? It tells you how fast can the clocks grow. Can the clock goes? Right? Because if you feed the clock too fast, the circuit might not be able to finish in time. Then you start the new instruction, but wait, I'm not finished.
Yeah.
You are in trouble. Mhm. Uh-huh. So when we said, when the vendor say, oh, our processor support about 1 gigahertz, that means if you put 2 gigahertz in, it may fail because of the critical part like this. Okay, and I didn't do the calculation, but if you got like what I cannot remember, 40, that would be 100, 110, 120, 220, 230. Let's say I make up the number, okay, 240 nanoseconds. I make the number. I didn't do the real calculations. If we got like what 240 nanoseconds, how fast is the clock? Okay, let me just go back. The critical part is 240 nanoseconds. How many gigahertz of clock can I put in? How to calculate that? Frequencies is 1 over period. So you got what 1 over 240 to what? Minus 9, right? You convert that, you would get hertz. And this is the fastest clock that you can give for this processor. Got my point? The fastest clock determined by the critical part, the slowest part.
So like more than this, just to get some.
More than this, some instruction like store may fail because the memory might fail to write and you start a new instruction. For example. Mhm. Are we okay? So I know it's a lot of information for a day, but if you have strong background in digital circuit, this is simple. Uh-huh. So I do not blame you for that, but at the minimal, make sure that you understand how we construct data part. Identify the control signal. And with that, I'm happy. Ignore the digital circuit details. Never mind. Okay. Don't mind the digital circuit details. Make sure that if I give you an instruction set, you can construct data part. Okay. That's enough for this class. Good enough for this class. Yes, some picture like this, data part. So I will give you instruction set architectures. Explain in RTL. Oh, this register, go to that register, do this operation. Now, you give me the data part. Once you give me the data part, identify the control signal. Okay, fill the tables, then do the critical part, and that's it. I'm happy with that. For other parts, just ignore them. Okay, you have question? No, then I got few exercise that might help you. Again, this is from my point of view, very simple, stupid processor because it's got CPI equal 1 and very long cycle. Bad design in a sense, but just to get you the idea about how to make the data part. Okay. Later on, we will try to make it faster. I mean, next week, we will try to make it faster and we will learn how. All right. Few exercising. Okay, let's try this one. I say our single cycle processor got critical path at 230 nanoseconds. If I run a software which contain 2 million instructions, what is the CPU time? Yeah, okay, good. So how does it work? So this is what, 2 million to the 10 6 to the 6. And since this is single cycle instruction, this is 1. And what is the cycle time? 230 to the 10 minus 9.
Single set.
Single cycle processor, that's why it's 1. Okay, you do the math. Really simple. All right.
4.6. And the total of size.
Yeah, 4.6 something. Yes. Okay, good. Okay, I think I have another one. Oh, this is maybe not for you. No, you cannot do this. You cannot do this. You cannot do this. Okay, no. For what? Like this one and this one? Okay, I can do that, yes. But will you be able to understand like what is PLA? If you have no idea what is PLA, then we have another problem. Eh? Programmable logic array. Maybe not. All right, just ignore this one. Okay, that's not for you. And ignore this one. This is not for you. And we will not have something like this in the examination. Okay. Right. Because you cannot do it, or else I have to go back and teach you the missing part in digital circuit that you should have learned 2 years ago. That too much. I mean, it's not the focus of this class. Okay. Anything you want to ask me before we call it a day and I let you go? All right. You might want to review a little bit. Next week, we will try to make this CPU go faster. Okay. This is simple, stupid CPU, and we will make it better. Okay. So I would stop here then.